In this video, we are going to talk about, or we're going to review about energy fundamentals, what are the units of energy and power as well. And it's just a basically brief overview or review of your previous knowledge on energy and power, the different transformation, and some example calculations. So, as we all know, energy is basically the capacity to do work. And as we remember for our physics days, physics education, work is equal to force times distance. And the main unit for energy is in terms of joule. Joule is signified by J as its unit. This is energy exerted by a force of 1 Newton to move an object by 1 meter. So this is force times distance. So basically 1 joule is equal to 1 Newton meter, or you can also expand it into in terms of kilogram meter per second squared. So 1 Newton meter or 1 joule is equal to kilogram meter per second squared is Newton and times the meter. So it becomes kilogram meter squared per second squared. So that would be the unit for joule. In the same way, the power, as we all know, is just basically the rate of energy that is converted to work. So this is a rate at which energy is converted or work is performed. So in terms of equation, energy is equal to power times time. So when you say rate, it's just a unit per is a rate per unit time. So it's energy per unit time. So it's just basically power is just energy E over time. So if we have E as energy is in terms of joule, so joule per time, and time is usually in seconds. So 1 joule per second is watt. So this is the unit of power, the watts. And so 1 watt is also equal to 1 Newton per second, or equal to 1 kilogram per square meter per cubic s cube. So these are the two main units of energy and power. And as you can see, this is just a diagram showing the conversion of energy into different forms, and which we are going to talk about in the first law of thermodynamics. And so the conservation of energy coming from chemical energy, going to electrical energy, conversion to kinetic energy. And so basically, energy is not lost at all. It's just being converted into one form and another. So the main unit for electrical energy is kilowatt hour, kWh here. So when we talk about electrical energy, we refer to kWh or kilowatt hour. So 1 kilowatt hour is basically the amount of energy consumed by the device for drawing 1 kilowatt of power over a 1 hour period. So if you look at in this diagram here, for example, you have power on the y-axis and time on the x-axis. So this part here is basically the same area as this area here and as this area here. So all of these are actually has the amount of energy as electrical energy as 1 kilowatt hour. So it's exerted at 2 kilowatt power for a period of half an hour. So the result is still 1 kilowatt hour. Exerted a 1 kilowatt power for a period of 1 hour is still 1 kilowatt hour, or you exerted a power of 0.5 kilowatt for a period of 2 hours, then you still have 1 kilowatt hour of power. So it depends exactly on how much power for extended period of time is being exerted on a specific device. So for 1 kilowatt hour is when we convert that one into megajoules, then 1 kilowatt hour is basically equal to 3.6 megajoules. So it's just a matter of conversion of units. So 1 kilowatt hour, so we convert the hour into seconds, and then we convert we cancel the seconds from watts, which is joules per second. So an hour is 3,600 seconds in 1 hour. All right, so we can cancel hour now. So we have 3,600 kilowatt second. Now, since kilowatt is 1,000 of watts, so it becomes 1,000 watts, which is joules per second. So 1,000 joules per second times second. times 3,600, which is this one. So now we can cancel seconds, and then we can get 3,600,000 joules, or 3.6 megajoules. So this is a very important conversion unit. So please try to remember 1 kilowatt hour is equal to 3.6 megajoules. So for example, here, if we're looking at these examples that I mentioned here, so an electrical for 1 kilowatt hour, so it can be an example as an electrical heater rated at 1000 watts or 1 kilowatt operating for 1 hour uses 1 kilowatt hour of energy, which is basically this part here. So a television rated at 100 watts operating for 10 hours uses also 1 kilowatt hour of energy. All right. So you have to remember this is basically a function of the power and the number of hours of use. So a 40-watt light bulb operating continuously for 25 hours also uses 1 kilowatt hour of energy. But what is the difference between this kilowatt hour and watt per hour? So it's basically different, of course. So when you say watt per hour, is basically the change of watt in per hour. So this is the unit of change of power per hour. So a power plant reaching 1 megawatt from 0 megawatt in 15 minutes. So the change of from 0 megawatts to 1 megawatts in 15 minutes has a ramp up of 4 megawatt per hour. Okay, so it means that it's increasing at 4 megawatt per hour when it is increasing from 0 megawatt to 1 megawatt in 15 minutes. So this is different. This is the rate of change, of your power per unit time. This one is the energy that being used of your device. So there are other suffixes or prefixes that we can use to signify the unit of the energy or power. So please remember some of these. For example, 10 to the 15 is a prefix of peta. So when you say 1 times 10 to the 15 of joules, so you can say 1 petajoule, right? Because this is 1 to the 15. Also, terajoules is more important. 1 times 10 to the 12 joules is 1 terajoule, okay? Or 1 terawatts if it's watts. Giga is 10 to the 9, 10 to the 6 mega. Most of the energy and power are in this range here because they are big amount. These one are not very, very useful at this point because they are just very, very, very little amount. So these are what we use in energy calculations. Of course, this is just a summary of the different units for what we will use in our discussions here. For the force, the unit of force is Newton, or it could be in English form as pound force. But usually we use Newton here. Energy is in terms of joule, and if in terms of electrical energy, we use kilowatt hour or megawatt hour. Power is in terms of watt. Sometimes we use horsepower as well. And these are some of the conversion as well. Ton oil equivalent is converted to 1.5 ton hard coal. BTU is energy to heat 1 pound of water by 1 degree Fahrenheit. So BTU conversion unit is 1.055 kilojoules. So we can have a different conversion unit for different units of energy, or SI unit or English unit. So let's have a simple unit conversion example for two problems here. So the first one is a direct conversion problem. So if a system produces 1 BTU of energy, so BTU is a unit of energy, every minute, so we have a given time here every minute, what is the power produced in watts? Of course, the question is power. And so from here, everything is given. So once we know the equation or the description of power, power is equal to the rate of change of energy. So this is energy per unit time. And so based from the conversion factor, or conversion of 1 BTU is equal to 1055 joules, or 1.055 kilojoules. So that is based on the previous slide. As we all know, this is the value of conversion of BTU to joules. So we have energy as 1 BTU, and then time is 1 minute. So we just input 1055 joules per minute and then convert minute into seconds. So the conversion factor is 1 minute per 60 seconds. So we can cancel out minute now. So the answer is 17.6 joules per second, which in this case is 17.6 watts or 18 watts for if you round it off. So this is a very simple one. The second one is another example is how much energy in kilojoules would a 75 watts light bulb use in 24 hours. So now we are converting this power into energy. So the same way, since power is equal to energy per unit time or over time, therefore we can rearrange. So we can have energy is equal to power times time. So since we are given the power and we are given the time, so we can just directly substitute these values. So 75 watts times 24 hours. But just make sure that the units that you are using are consistent and are similar with the units there in all units of the equation. So in this case, watts is in terms of joules per second, right? So what is joules per second? This is hours. So we need to convert hours into seconds. So we can do it from here, 75 watts or joules per second. We can even convert the joules into kilojoules. So 1 kilojoule is 1000 joules. Times 60 seconds is 1 minute per 60 seconds is 1 minute, and then 60 minutes in 1 hour, and so we can multiply with hours. So we can cancel the hours, we can cancel the minutes, and what is left is basically seconds here. All right, and then the seconds here can be canceled out with the seconds here as well, and then the joules can be canceled with joules. So what remains is kilojoules. So the answer is 6,480 kilojoules, or rounded off into 6,500 kilojoules or 6.5 megajoules, because 1 megajoule is 1,000 kilojoules. So that's the final answer, or this is the final answer because they are asking for kilojoules in units. This is another problem or example problem that I just wish to give you as well. Conversion between energy and power. Two problems on the conversion of household energy use. Like for example, in this example, we have in our household, for example, the bill that we get from the electricity provider is in terms of kilowatt hours, I mean. So we have electricity usage around 20 kilowatt hours per day, and the gas bill is in terms of joules, that was given in joules, so 30,000 kilojoules per day. So these are the energy consumption of a certain household. So the question is, for this problem, is what is the total energy use in one day? So you can decide which energy unit you will use. It could be in kilojoules or it could be in kilowatt hours. So you decide for that if both units are in terms of energy. So you need to at least convert one of these units into the same unit for both. And what is the average power consumption per day? So you need to, once you get the total energy, then you need to find the power consumption for the whole day. The second example is on the still on the power and energy conversion. So you have a 60-watt bulb or LED, and it is used for 8 hours. So it can be two types. You have a bulb type, incandescent bulb, and the other one is LED type. And both are in 60 watts of power. They can produce 60 watts of power. So the incandescent type of bulb is actually, the majority is heat. Okay, 95% is heat is generated, and only 5% is light. Okay, so there's a bit of conversion now in terms of the electrical energy towards heat energy and light energy. The question is, how much is the total energy, right? It's a question of how much is the total energy if these are your given only. And how much is the light energy, how much is the heat energy. And also for LED, instead of 5% light, it is now 15% light. So it means the LED has 85% heat and 15% light. So it means the conversion now is higher for lighting when you use LED, and only smaller amount of heat are coming out of the light. And the question is, what is the implication of both of the answers that you have if you are to choose for winter or summertime? So what will be the implication of the usage of these two for different seasons? So let's take this one for an example in the next page for the solution. So the first example is about the total energy used in one day and the average power consumption in per day. So we know that we are given 20 kilowatt hours per day. The other one is 30,000 kilojoules. Then I decided to convert this kilowatt hour into kilojoules. So in order to do that, we can just basically multiply with conversion factors. So we have 1000 watts per kilowatt, so that we can cancel the kilowatt here. And then 1 joules per seconds per watt, so we can cancel watt here. And in 1 hour, we need to cancel the 1 hour here. We have 3600 seconds in 1 hour, so we can cancel the hour. So what happens now is that the second here also cancels the second here. So what happens is the remaining unit is joules. So if you multiply this one, it becomes 72 million joules, or to make it kilojoules, it's 72,000 kilojoules. Now you have now the same unit as the next one, kilojoules as well. Then you can now add this both. So 72,000 kilojoules plus 30,000 kilojoules is the total energy is 102,000 kilojoules. Now, since we have the total energy now, we can now solve for the average power consumption. So that is per consumption per day. So that means we can divide this amount, total energy, with 24 hours in one day. And so this is hour, we can convert into seconds. So 1 hour is 3600 seconds. So we divide this in this denominator here. So the answer is 1.18 kilowatts. So that's the average power consumption for the both electrical and gas usage for that household. Okay, the next example is on the comparison of the energy usage between LED light and the incandescent bulb. So we have 60 watts of power for bulb or LED, and both are used for 8 hours. So we need to compare the usage of these two. For incandescent bulb, the heat takes up 95% of the total energy output. From light is only 5%. But for LED, heat is 85%, so there's a reduction of heat loss. But light is 15%, so it's brighter now using LED. We will compare the energy usage or the use and what is the implication for summer or winter. So the first step is to calculate the total energy. We are given 60 watts here, and for 8 hours of use. So what is the unit of energy? So the unit of energy is joules or kilojoules or kilowatt hour. So we can choose to put that into kilojoules. So given of power is equal to E over T. So energy is now power times time. So we're given a power of 60 watts or 60 joules per second times the time of 8 hours, which is 1. And we can convert 8 hours into seconds. So 3,600 seconds per hour. Multiply all, cancel hour, cancel second. So what is remaining is joules. So it's 1,728,000 joules or 1,728 kilojoules as a conversion. So this is the total energy now for that light, for that bulb or LED, okay, for that light source. For the bulb, using the energy balance, so basically the total energy is basically a summation or the total of heat plus the light energy, right? So the heat and light energy. So for the light energy that is coming from that bulb, is only taking 5%, as it mentioned here, 5%. So only 5% of the total energy. So if you have 5% times the total energy, which is 1,720 kilojoules, so we can multiply with 5%. So it means the energy needed for the light alone is 86.40. And so with energy balance, so it means 5%, the remaining is for heat. So we can just subtract with or reduce, subtract this amount to the total energy. So 1,728, which is the total energy, minus the energy for lighting, is equal to 1,642 kilojoules. So this energy is lost as heat. All right. So this is higher heat loss for the use of high heat loss for incandescent lamp in the bulb, I mean. So for LED, the same way we can do the same, but now it's 15% times the total energy is 259 for lighting, and for heating is 85% times the total energy is 1,468. So this means that light LED is more efficient in brighter light because it produces more light or more energy for light compared to heat. So the implication is one. Implication for summer or winter, we can say that because the incandescent bulb is releasing more heat, so this bulb is better to use during winter time. Because if we put the bulb on winter time, it means we can heat up the room without using other source because there's a heating of energy coming from the bulb. All right, so LED is not good for winter time between the two because the heating is lesser compared to incandescent bulb. So this is just a quick example of how we can convert energy and power and vice versa. So if you look at some of the things and put into perspective how much is the quantity of energy or power in terms of power. So we can see from here that a human heart is around 1 watt of energy, can produce 1/2 or requires 1 watt of energy. And for the light bulb, it can produce 100 watts of energy. And of course, we just made an example of this, not all light. The conversion is there's also heat, a lot of heat that is lost from that energy. We can go farther and make it bigger. So for a large wind turbine, we can have 2.5 megawatts of production of energy production. If you're much bigger for coal-fired power plant, normally it's around 1 gigawatt. And so in comparison, the world average power generation is around 18 terawatts. So it means if you divide this one with 18 terawatts divided by 1 watt, so we are experiencing a large number of human heart production, energy, power production in order to produce the same amount for the whole world. So we can see from this example the magnitude of different values of power. So we can divide energy into mainly two different forms. The first one is potential energy and the other one is kinetic energy. I think everybody knows about this. This is a very fundamental aspect of energy. So potential energy is based on the position. So the higher you are from the ground, you have more potential energy. So the farther you are from the ground. So the equation for potential energy is equal to mass times the gravity times the height or the elevation. So it is directly proportional to the elevation. So the bigger or the higher the elevation is away from the ground, you have more potential energy. On the other hand, so it is more static energy. Kinetic energy is associated with motion. It's the movement. So basically the fundamental equation is energy is equal to 1/2 mv squared, and m is the mass and v is the speed or velocity raised to the power of 2. So of course we know the unit of energy is basically joules, and also here is joules or kilojoules. So these forms of energy can be further subdivided into other forms of energy. So potential energy is a stored energy. As I mentioned before, it's based on position or gravity. And there are a number of forms or kinds of potential energy. One is chemical energy. This is the energy in the form of stored in the bonds of atoms and molecules. So this is the energy stored in a substance, basically. So biomass has chemical energy. So biomass could be wood. So wood, we can burn the wood. So the energy is released upon burning. Petroleum has a stored chemical energy. And basically, fossil fuels have stored chemical energy. And coal also has very high energy density. Nuclear energy is also stored in the nucleus of an atom, so it has a very, very big energy density for nuclear energy. Also, we have the gravity is also mainly a potential energy in terms of the position. So, in hydropower, we have the use of gravity of that energy from the position of the water that goes down from a reservoir towards the turbine to power the to pump to power that turbine to produce electricity. The other one is kinetic energy, which is based on motion, and radiant energy is one based on electromagnetic energy that the light travels and heat. Thermal energy is based on the heat, the internal energy in substances. So this is based on vibrations. Geothermal energy is an example of this thermal energy. Of course, there's a sound also is a form of kinetic energy, and electrical energy is the movement of electrons. So it's also a form of kinetic energy. So these are two main forms of energy, potential and kinetic energy. So we can have an example conversion of both or a sample calculations for both types of energy. The first question is, what is the kinetic energy associated with a 1,500 kilogram automobile traveling at 100 kilometers per hour? And so it's a pretty direct input of values. So what is the formula for kinetic energy? Energy is equals to 1/2 mv squared. So 1/2 is 0.5. The mass is given, which is 1,500 kilograms. So we have 1,500 kilograms times the velocity or the speed. So in this case, the unit of velocity was given in kilometer per hour. And so we want to convert this unit into a form that is gonna result in joules. So that form is in terms of meter per second. So we can convert kilometer per hour into meter per second. So 100 kilometer hours per hour convert to seconds is 27.8 meter per second. So conversion factor is 1,000 meter per kilometer and 3,600 seconds per hour. So we can get 27.8 meter per second. So now we have all the values, put them together, and we can see that the final answer is 5.8 times 10 to the fifth kilogram meter squared per second squared. And this kilogram meter squared per second squared, as explained in the first few slides, is equal to joules. So this is basically 5.8 times 10 to the fifth joules. So that is the final answer for this question. The second example is about a 75 kilogram person walks up a flight of stairs with a vertical height of 3 meters. What is the change in that person's potential energy? It's very simple. Mass times gravity times h, or height. So in this case, mass is 75. The gravitational force is 9.81 meter per second squared. And the vertical height is 3 meters. So all in all, if you multiply this one, it becomes 2.2 times 10 to the cube joules. So it's pretty much straightforward, but both of them are very important equations to use later on, especially for hydropower, this one, and this one is for the wind energy. So there's another example here for I'm just putting a number of simple calculations because it's better to be at least a simple review of what you have learned previously in your undergraduate years or some previous years in terms of calculations. So here 1 liter of water is poured off a 50-meter high tower every second. If the change in gravitational potential energy is converted into electricity with an efficiency of 86%, how many 60-watt light bulbs can be illuminated? So it's basically the question is about converting this, the output electricity into the number of 60-watt light bulbs that can be lighted up. All right. So how many? So the final question is how many of these light bulbs can be lighted up or illuminated based on the output electricity here. So from this equation, from this problem, we can use the equation of potential energy, right? Because this is gravitational potential energy. So potential energy is E equals mgh. So we have the mass of water, which is 1 liter of water. So where is the mass? 1 liter is the mass. So 1 liter, the density of water is 1,000 kilogram per cubic meter, right? 1,000 kilogram per cubic meter. And 1 cubic meter is 1,000 liters per cubic meter. So because of that, this 1 is to 1. So 1 liter is actually 1 kilogram equivalent. So I think everybody knows about that conversion. If it's water, 1 liter of water is equal to 1 kilogram of water. So that is the conversion of that because the density is 1 is to 1. So with that, we have 1 kilogram of water here. And then we have the gravity of 9.8 meter per second squared. And then the height is 50 meters. So the energy produced is 490 joules. And then we are given an efficiency. So in this case, the efficiency is 85%. So the efficiency 85%. So with that efficiency, we can calculate for the electrical energy. So efficiency is basically how much the actual amount of energy that is produced. In this case, we can multiply the energy times the efficiency is equal to the energy output, the final energy output of 417 joules with respect to 85% efficiency. So if this energy is produced every second, as mentioned here, every second is the time is given there. So that means that 417 joules per second, per 1 second, it becomes the power now. So with 1 second, it becomes 417 watts now. So we have the final power output for this problem. So now the question is how many 60-watt light bulbs can be illuminated. So what we can do is basically just divide this one with the capacity of that light bulb. So this one is 417 watts divided by 60 watts per bulb, right? So watts can be cancelled, the bulb goes up, so it means that it's around 6.95 bulbs or 7 bulbs in total for that amount of power that can, for that amount of power, you can illuminate around 7 bulbs in total. So in any energy discussions or any energy overview, we need to look at the laws of thermodynamics, especially on energy transfers. So we look at only 2 of the laws of thermodynamics. The first one is on the first law of thermodynamics, is energy cannot be created nor destroyed. It can only be changed or it can only transform. So this is the first law of thermodynamics. Basically, it's a law of conservation of energy. So energy cannot be lost. It's somewhere there that is only transformed. It cannot be destroyed at all. It cannot be created. It's just transforming from one form into another. And I think Everybody knows this. So for example, if you have heat energy, can be transferred into mechanical energy, or it can be transferred into electrical energy, and maybe loss of heat along the way. So it's just a mere transformation rather than destroy or creation. The second law of thermodynamics, and I think it's very important as well, is that energy will always transfer from high to low, like any heat transfer, from high temperature to low temperature. And the one word definition of the second law of thermodynamics is entropy. There's always losses. Okay, there's no like 100% highly efficient. There's always losses along the way. So no energy transfer is 100% efficient. Entropy is basically the loss or disorder. Okay, so what it means that, for example, in coal mining, if you get a large amount of coal, that total energy of coal will have to have not to be 100% efficiently used to create the electricity at the end. So we'll take a look at that with the energy transformation. So I've mentioned before, for a primary energy source like coal, let's say for example it has 100 units of energy in this coal stored energy. All right. So once the stored energy is processed and um, make use as a fuel to generate in power plant, for example. So the power plant in generation, then along the way, the loss of from 100 units of energy, about 70 units of that is lost as heat during the processing. All right. So what happens is that only 30 units of energy is remaining. And then now, upon electricity generation in this power plant, it goes towards the transmission. Okay, so towards the grid. So along the grid, about 6% or 6 units of that is lost as heat. So normally heat is the other transformation here. So 6 units is lost. So what happens is from 30 it becomes 24 units now. All right. So in 24 units, it is now being lighting into use bulbs or LED. As I mentioned in our previous example, the light bulb can generate heat up to about more than 90%. So in this case, from 24 units of electricity that is generated, once it is converted into the homes and used as light for the incandescent bulb, then almost more than 90% of it, around 22.8 units here, is lost as heat. And only about 1.2 units of energy is used as visible light. So you can see how much reduction in terms of energy along the process here. So that's entropy. There's a lot of reduction of energy or transformation energy and loss of energy along the way. So it's basically the same as the overall energy conversion and transformation. From the energy source, there's energy conversion and losses as well, and then only a small part is useful energy. Okay, so the same way for this example, which is pretty much similar. There's thermal energy coming into the house. There's electricity coming into the house. There's gas coming into the house with chemical energy, and they are being transferred into different forms of energy, like use as electricity to power fans, washing machines, refrigerator, to heat the oven, and many of these transformation is lost as heat along the way. So that's why we can feel some heat in our house if we use a lot of appliances. So the same way, there are conversion efficiencies for different kinds or different types of energy technologies. So in this case, for example, in power plant steam turbines, from chemical fuel and into transform into heat, the efficiency is around 90 to 98%. So it's pretty high efficiency. Generator wise, from mechanical to electricity, has quite high efficiency as well. But if you look at some of the renewable energies, the PV cells or photovoltaic cells, from the light source, the solar light, into electricity, the efficiency is actually 10 to 15%, but now it has increased to around 25%. So it's increasing, but still, if you compare with other fossil fuels, this is a very low efficiency energy technology. So we need to increase the efficiency to this. Hydro is pretty high, it's very stable. The wind has also around 40-45% efficiency. And so comparison to PV, this needs more advances in terms of material and overall performance efficiency. So what I'm saying here is that the transformation can lead to a lot of losses from transforming from one form of energy to another. So the conversion will lead to a lot of losses along the way. There are two kinds of energy that is used and produced. The first one is primary energy, and I think everybody knows about what's primary energy. It's energy that is directly harvested from nature. So in this case, most of the fossil fuels are primary energy, like the coal, the oil, and natural gas are coming from nature directly. So these are 95% of our primary energy is coming from the fossil fuels. The rest are coming from renewable energy like hydropower. The wind power is also from nature. The sun, sunshine is solar power, and also the tides is also primary energy. The other end of this term is end use energy, is basically the one that the consumer is using. So primary energy is transferred into end use, but the amount of energy you have here as shown in the previous slide is much bigger compared to the end use energy because a lot of losses along the way. And so this is the energy directly consumed by the user. So it is in the form of electricity or gasoline, because gasoline is already a processed fossil fuel. And so the typical power plant is around 33% efficiency. So what I mean is that the primary energy coming from here, it consumes 3 times as much energy in fuel, like coal, as the amount of energy produced as electricity. It means that the energy coming from here is degraded or smaller when it comes to an end-use energy. And this shows here the various contribution of different types of primary energy sources around the world. The coal is also 29%. Coal and oil are fossil fuels, so they are, as I mentioned, is more than 80% are given or are supported by fossil fuel in the whole world. So basically what I have presented here is just a very basic summary, a very basic overview of energy, the fundamentals of energy. And some of the main equations have been given here. Basically more equations and more discussions about energy fundamentals will be tackled and discussed in each energy technology that we are going to talk, like solar energy. There will be a number of calculations there. On wind energy, we will also use kinetic energy calculations there. And so we are going to give more discussions in the later parts of our lecture. So as a summary, as we know, energy is the ability to do work, and power is just the rate of energy change. So that is per unit time. And there are a number of different category of energy. It could be kinetic, potential, and thermal, nuclear, electrical. And the first law of thermodynamics is about conservation of energy, which means that energy cannot be created nor destroyed. It's just transforming. And then there's always a loss in the system. So coming from the primary energy source towards the end user supply, we'll have a lot of loss throughout the system. And fossil fuels can be used to generate electricity in thermal generating stations, which consist more than 80% of the world energy supply. And different energy sources have various performance efficiencies, and renewable energy technology is still quite low in terms of its efficiency, especially solar PV. Wind is better at 40%, and hydro is much better at more than 80%. But the newer ones like PV and other new energy technologies are quite low in terms of efficiency and still need to be improved so that it can increase the more uptake and more higher energy density to be given as a better contribution to the overall energy mix. So I end the presentation for this time.